Hello everyone, welcome back. We are in the third lecture and our topic is free vibration. So, we have a single degree of freedom system where there is a spring connected to a mass, and we also have a dashpot. So, the mass is m, spring stiffness is represented by k, and then c is the damping coefficient. Now, the degree of freedom in this case is 1, which is x of t, and for this Hausdorff system we have derived the equation of motion mx double dot plus cx dot plus kx is equal to 0 in this case, because we are solving the homogeneous part, otherwise there will be a forcing function, and in this case it is a initial value problem. So, we have two initial conditions defined at t equal to 0. So, displacement and velocity at t equal to 0 is given. Now, for that we have solved two different cases. The first one is obviously the undamped case, that means this second term, the damping term, we do not consider. So, the first problem we have solved is undamped case, and for that we defined one important structural parameter called natural frequency omega n, which is equal to square root of k by m. And then for that the solution x of t has this form r cos omega n t minus theta. So, r is the amplitude and theta is the phase, and omega n is the natural frequency with which the system oscillates. In this case, if we plot the nature of the response x of t, as t progresses it will continue oscillating, and it continues with t because there is no damping. The system once set in motion will continue with its motion. Now, the second case where we have damped condition, then we defined another parameter eta, that is the critical damping parameter, which is C by Cr. Cr is the critical damping. So, the ratio of the damping with its critical damping is the damping coefficient, damping ratio, critical damping ratio. So, if this is 1, we have critical damping. If it is greater than 1, we have overdamped system. And if it is less than 1, we have underdamped system. And in all these three cases, we have solved the response of the structure x of t, and we studied their nature also. And if you recall, only in the third case where we have underdamped system, we have structural vibration. Otherwise, in the first two cases, structure does not vibrate, it starts its motion, but asymptotically reaches 0 line as the time goes to infinity. Now, when we have the underdamped case, then in that case, if you recall, we have solved lambda 1, lambda 2, that is the root of the characteristic equation once we assume some trial solution. Then lambda 1 and lambda 2 was eta omega n plus minus I omega d. And the solution for this case, if you recall, x of t will be equal to, it is r, then e to the power minus eta omega n t, then cos omega dt minus theta. So, if we compare these two solutions, one for undamped case, another for damped case, you can see the difference. In both the cases, we have r cos omega t minus theta, because in case of undamped we have omega n. The moment we have damping, that omega n is replaced by omega d, because we will have damped natural frequency, and the oscillating solution is actually modulated by this exponentially decaying function. Now, if I quickly draw the solution, in this case we have, as t progresses, then we have exponential decaying envelope, and within that we have solution of the system. And it continues. So, this line represents e to the power minus eta omega n t. So, up to this much we developed in our last class, but if you just quickly note the nature of these roots. So, lambda 1 plus lambda 2 will be what? If we just add them up, so this will be minus twice eta omega n. And lambda 1 minus lambda 2, obviously you will be having twice I omega d. Now, if you look at the complex plot, so we have, this is real of lambda and this is imaginary of lambda. Then we have omega d marked here, and then this is our minus eta omega n, and the root in the complex plane will lie here. So, this is our lambda 1 and this is our lambda 2. So, what is omega n? Omega n in terms of the roots, it is square root of lambda 1, lambda 2, and what is eta? Eta is equal to minus lambda 1 plus lambda 2 divided by twice omega n. You can easily prove this, it is very simple from the expression of this roots that we have derived, you can easily prove this. So, that tells us when we have free vibration, how the system behaves under the influence of damping. Now, if we revisit the same, so we have free vibration and we have damped case. Now, in this case, if you look at our x of t is equal to what? R e to the power minus eta omega n t, then cos omega dt minus theta. Let me quickly redraw the response again, because we are going to use that to identify the damping of the structure. So, we will see how this solution behaves. So, we have this exponential decaying envelope, and then we have the response. Obviously, this first part, this is the x naught, and the velocity at this location, at this point is given by this tangent, which is x naught dot. So, this is this velocity. Now, let us consider this response. Just imagine if we have a SDOF system and we can measure the displacement of that system, we basically get this plot. Now, from this plot we can identify the structural parameters. What are the structural parameters in this case? We have natural frequency, we have critical damping ratio. So, for that let us see how we can evaluate. So, let us consider, say, this point is T1. So, at T1 we have this response. We can consider any time point. So, this is, say, x1 at time point T1, and we consider the point T2. At this point the response is x2, but obviously because of the damping the response has reduced from x1 to x2, and what we can also conclude that T1 minus T2 is the time period. So, if we can identify time period from this measured displacement, then we know T is equal to 2 pi by omega n. So, from this relation we can find out what is the natural frequency. So, that is the first information we get if we have a SDOF system and if we can measure the displacement corresponding to free vibration. Now, that is not the point I want to explain here. What we can note is that we have two time points T1 and T2. Now, these two time points are one time period apart. So, what will be the response? So, x1 is r e to the power minus eta omega n, then T1 cos omega d T1 minus theta. So, that is the response we get at time point T1. So, this is x1. Similarly, we can also write down x2. x2 will be what? R e to the power minus eta omega n T2, but T2 is T1 plus capital T times cos omega d T2, that is T1 plus T minus theta. Now, if we take the ratio of x1 and x2, then what will happen on the right hand side? Obviously, the r will get cancelled. So, we will have e to the power minus eta omega n T1 divided by e to the power minus eta omega n T1 plus capital T. And because the remaining part is a cosine function, and if we consider its value at one time period apart, obviously they too will be equal and they will obviously get cancelled. Now, we can further simplify this expression. So, if we do that, if we open this bracket in the denominator, so e to the power minus eta omega n T1 will get cancelled and we will be left with e to the power eta omega n capital T. Now, on the right hand side we have an exponential function. So, if we consider log, so ln of x1 by x2 is equal to eta omega n t. Now, I will slightly modify this notation, because in reality when we have damped free vibration, the time period that we get is T d, not exactly T. So, this relation will be modified. So, we will have T d here, and then obviously corresponding natural frequency will be omega d. So, from this relation we can find out omega d. We will find out omega n in a minute. So, this relation ln of x1 by x2 equal to, on the right hand side we have eta omega n T d. Now, what is the relation between omega d and omega n, if you recall? So, we have omega n 1 minus eta square. Now, if we find out what is omega n times T d, we have omega n, in place of T d we can write 2 pi divided by omega d, and in place of omega d we can use the relation omega n then 1 minus eta square. So, this omega n will get cancelled. So, ultimately what we are left with is omega n times T d is equal to 2 pi by square root of 1 minus eta square. So, that if we put in this expression, what we have ln x1 by x2 will be equal to eta, in place of omega n times T d we have 2 pi divided by 1 minus eta square. Now, on the right hand side, if you notice, this is a non-dimensional constant. So, we call it delta. So, in the logarithmic scale, what is this delta? This is called logarithmic decrement. So, this is called logarithmic decrement. So, as time progresses, obviously the response reduces because of the presence of damping. Now, if we look at this response quantity, so this response quantity if we can measure, then from that first we can identify this damped time period, and from there we can find out what is the natural frequency, damped natural frequency. And then if we consider two time points T1 and T2, then obviously using the displacements at T1 and T2, that is x1 and x2, we can now develop this expression what you have on your screen, and using this expression we can find out the value of eta. This is called logarithmic decrement. Obviously, if we have eta which is much less than 1.0, then we can further simplify. So, our delta is equal to ln x1 by x2, which is approximately equal to twice pi eta. So, that is the relation we have, and the technique thus is called logarithmic decrement technique. So, in this technique what we do? We measure the free vibration response of a SDOF system, which is having damping, and from the plot we can find out the damped natural frequency. From this plot, this is the measured response. From this measurement, we can find out damped time period. From that damped time period, we can find out damped natural frequency, and then if we consider T1 and T2 using the displacements x1 and x2, we can find out ultimately the critical damping ratio. So, the moment we find out critical damping ratio, then again using this relation of damped natural frequency and natural frequency, we can find out omega n. So, that completes the exercise. So, we can measure the response, and from that we can find out the critical parameters, the modal parameters of a SDOF system. The two parameters are natural frequency and critical damping ratio. We will solve some problem, we will see how we can apply this for measured response, but for the time being, the technique we have learned now is called logarithmic decrement technique, that uses damped free vibration to find out the parameters of the system. Now, if we, before we close our discussion today, if we look at the damping, so for damping we have different models for damping. We have different options for damping actually. So, the first one is what we call structural damping. The second one is viscous damping. Third one is what we call Coulomb damping, and fourth one we have, in some cases we have negative damping as a very special case. Out of that, in our entire course we will consider viscous damping, unless we specify, we take some special examples, we always consider viscous damping. Now, in this case, the damping force F d is proportional to the velocity. Now, the model that we have developed for SDOF system, we have actually considered this type of structural damping, this type of damping in the system. What is structural damping? It is due to the internal molecular friction of a material. So, at the material level we can model and we can quantify this damping. Now, sometimes in a structural system we consider different structural joints or different structural components also have interactions, and sometimes some inherent property of the structures are there which is actually modeled in this case what we call structural damping. Viscous damping we have already mentioned. What about Coulomb damping? In this case, this damping F d is developed due to friction. So, we have some normal force acting, and then obviously the frictional coefficient, if we can quantify, then using that information we can quantify this Coulomb damping. So, this is due to friction. And the third one, this is a special case. So, if the time permits, then I will show you some example of negative damping. But right now, I just want to show you how to model this Coulomb damping and what will be the nature of the solution if we have Coulomb damping. So, if we have a SDOP system, so in this case again we have a spring connected to a mass, but in this case the mass is actually sitting over a surface, and obviously when it tries to move it develops some kind of frictional force. Just note, in this case we do not have any damper as we had in the earlier case. Earlier case we had rollers below this mass and we had a damper, but in this case we have frictions developed at the interface. Now, if we draw the free body diagram of this mass, we have the weight, that is mg, acting downward. Then there will be a normal force balancing that, and at the interface now we will have the Coulomb damping force. And because of the spring, we will have a spring force which is k times x, and we will also have a inertia force which is m x double dot. So, now we have the free body diagram, and from this free body diagram we can develop the equation of motion. So, equation of motion in this case is m x double dot, then we have the damping force. I put a plus minus sign, I will come to that in a minute. So, the damping force F d, then plus k times x is equal to 0. And as usual we will have initial conditions x 0 and x dot 0. The question is, why we have this plus minus sign in the damping? Because in this case the damping force always acts in opposite to the velocity. So, that is the reason when we have positive velocity it is acting in one direction, when we have negative velocity it will act in the opposite direction. So, effectively what we have, if I write down the equation, so m x double dot plus f d plus k x equal to 0 when x dot is greater than 0, and the same with a negative sign when x dot is less than 0. Okay, so, in this case what will be the solution? So, solution in this case will be x of t is equal to a cos omega n t plus b sin omega n t plus f d by k signum function of x dot. The reason is we have two cases when x dot is greater than 0, f d is having a positive sign, while x dot is less than 0, f d is having a negative. So, that is the reason we have this signum function. So, if you recall, what is the property of the signum function? So, if we draw the signum function, it will be so, it will be plus 1 or minus 1, and at t equal to 0, it will also have 0 value. Okay. So, in this case, if we assume, say we assume at t equal to 0, x naught and the velocity is 0. So, let us set this is the initial condition, and then for that you can easily now solve this expression to find out a and b. These are the two constants we have in this trial solution, and obviously we can find out these solutions that you can easily do at your end just to satisfy these initial conditions. So, I leave it as an exercise. So, if we solve that, you will get a is equal to x naught minus f d by k So, that is your a, and b you will get 0. So, this is I leave it as a home task, you try it at your end. If you have any difficulty, then we can discuss in our open session. Only point I wish to draw your attention is that when you have signum function, when you try to differentiate, be careful, because at t equal to 0 you cannot differentiate this function. So, for that you just see what is the property of this trial solution and just take it as an exercise to find out these two constants. Let us see how it goes. If you have any difficulty, then we will solve it for you. Now, once you have this constants, you can then find out the solution. So, in this case, the solution is x naught minus f d by k, then signum x dot times cos of omega n t plus f d by k signum x dot. That is the solution in this case. Now, we have a SDOF system where we have Coulomb damping. That means, we have damping due to friction, and for that we have derived the equation of motion, and then we have also now the solution. Now, if you look at the solution, obviously we can plot this. On the right hand side you have this cosine term, that means it is oscillating, and then you can actually find out the period of this cosine function. In this case, it is again having omega n t is equal to 2 pi, and then you can qualitatively also plot the nature. So, that we will do in a minute. So, we have our response x of t. In this case, it is x naught minus f d by k sigma n x naught cos omega n t plus f d by k. So, that is the solution for the given case. So, if we consider the first half cycle, so obviously, in this case omega n t is equal to pi, and then you can easily conclude what will be x. It will be minus x naught plus twice f d by k signum x naught. So, that means if you look at this displacement, it is actually reduced by how much? By 2 times f d by k. So, in a half cycle it is reduced by twice f d by k. So, in the full cycle, this is in half cycle, obviously in the full cycle it will be reduced by twice of that. So, this is in full cycle. Now, if you plot the solution x of t, then again in this case we have the reduction of response as the time progresses. So, it starts from x naught. So, this is my x naught, and because x naught dot is 0, it will start from there and then it will continue. Now, what is this amplitude? This is x naught minus twice f d by k. That means, if it starts from x naught, in half cycle it will be reduced by this twice f d by k, and in the full cycle if we just draw a horizontal line here, then this reduction is 4 times f d by k. So, if we have a Coulomb friction, in this case also again we have exponential decaying sinusoid, we have vibration, but because of the presence of damping, again in this case as t times to infinity, the response will come to 0, and in every half cycle the amplitude reduction we have by a amount of 2 twice f d by k. Otherwise, the nature of the solution is similar to that what we have derived for viscous damping. The only thing is, in case of viscous damping we had e to the power minus eta omega n t as the amplitude modulation. In this case we have a different response reduction due to the presence of damping. Nevertheless, this shows you how we can develop different damping models, and then for that we can solve the response of the structure. Again I repeat, in this entire course we will use viscous damping. This is, I thought, to just give you an idea how to develop the equation of motion for Coulomb damping and what should be the nature of the solution. That is the reason I take this example. Otherwise, throughout the course we will be using viscous damping. Now, if I sum up, so today what we have learned is the logarithmic decrement technique. That is very important, because if you have a SDOF system, then if we measure the response of the system, from that we can find out actually the modal parameters of the system, and for that we use the technique called logarithmic decrement. There we consider the response at any particular time point, and then another response which is one time period apart, and then using these two informations, then we find out natural frequency and critical damping ratio. And then also we discussed different types of damping that we encounter, and out of that, if you have viscous damping which is due to the friction, then how to develop the equation of motion. We will solve one or two more problems on this topic, but otherwise our entire discussion will be based on viscous damping. So, with that, let us close here. In our next class, we will consider some examples and we will explore different problems that we have in free vibration. Thank you very much.